Normal intrapleural pressure at rest is. Good, that would be -5 centimeters of water pressure. Good job, Flo, taking the lead early. Laplace's law relates to which of the following? Good. So smaller spheres are more likely to collapse. And like you saw the illustration in your book, if you put a smaller sphere, a smaller alveoli next to a larger alveoli, that smaller one is going to require more pressure to keep it open. It's going to want to empty into the larger one. But of course, surfactant is the equalizer, so to speak. It makes the surface tension the same in all of them, so we don't have that problem. What is the formula for compliance? Good, that is your victory over pressure. Think about a cheerleader, be on top, okay? So victory and volume over pressure is always your formula for compliance. Taylor slowly. Osby's law states that if any airway diameter is decreased by half, then resistance will increase by. Good, 16 times. FRC can be described as. That would be the gas remaining in the lung following a quiet exhalation. So of course, a maximum exhalation following a maximum inhalation would be what?
Residual volume.
You are now unmuted.
Residual volume?
VC?
Well, VC is a max inhale followed by a max exhale.
Okay.
And then RV is what you can't exhale at all. So that's what's left in your lungs after a maximum exhalation.
So what was your question?
What's in red?
Max.
What is that describing? If anything.
Lung capacity.
Vital capacity?
Your inspiratory capacity?
Your vital capacity?
No, well, again, your vital capacity is a max inhale followed by a max exhale. Your inspiratory capacity would be an inspiration. This is describing an exhalation. So really, it's not a capacity. It would be your tidal volume plus your ERV, right? Because your tidal volume is what you can exhale normally, and then plus what you can exhale after a normal exhalation, that would be your tidal volume and your ERV together. So it's not an actual capacity, but it's those two volumes combined.
Oh, okay.
And then the gas remaining in your lung after a maximum exhalation is what?
Residual volume.
That's your RV. That's what you can't blow out. So after you blow out all that you can, what's left? RV. Okay, and then the maximum exhalation following a quiet inhalation
ERV?
Basically, yeah. So it's not worded this, but yeah. So maximum exhale. So assuming you inhaled, and let's assume that you exhaled that, and then what you can exhale maximally on top of that would be your ERV.
Oh, okay.
Okay, so make sure good job, Flo. Make sure you study those definitions. They will come in. Vital capacity consists of which of the following? Good, that will be all of the above. If you remember back to your box, if you've forgotten how to draw your box, I would suggest that you relearn it. Okay? Take some time to recommit that to memory. But if you're going by your box, of course, that would be your IRV, your VT, and your ERV all added together. Your vital capacity is a max inhale followed by max exhale. It's basically everything except what you can't blow out. So it's going to be everything except your RV. Okay, changes in FRC are an indication of changes in good. So changes in compliance. What kind of patients have an increased FRC?
Obstructive?
Obstructive people, good. Because that's the amount of air left in your lungs after a normal or quiet exhalation. These people tend to air trap. They tend to be hyperinflated. So, of course, they tend to have a larger FRC volume. And that's because their lungs are very compliant. They can accept large volumes of air, but they have trouble getting that air out. Which of the following increases compliance? Yeah, so this is another one of those questions that you could use process of elimination by figuring out which one is not like the other. So, of course, consolidation, pneumothorax, and pulmonary fibrosis all fall into the restrictive category. Emphysema is the only disease process here that's an obstructive disorder. So if you remember that, then of course that would increase compliance, or again, just process of elimination. All the other ones are restrictive. The only one that is not restrictive is emphysema. So of course it's got to be that one. You can't pick consolidation or pneumo or pulmonary fibrosis because they all act the same way. Does that make sense?
Yes.
How would you pick one if they all act the same way? You can't, right? It's not actually asking anything specific enough about that disease process to where you could distinguish one from the other. So if they all act the same way, you can't pick between consolidation or pneumo or pulmonary fibrosis. So it's got to be the one that acts differently, which is emphysema. Or, of course, you could just recall that emphysema is an obstructive disease, and obstructive diseases cause an increase in compliance. So you could kind of go about answering that question in two different ways. Probably more, depending on how your brain works. Which of the following devices is used to measure VE? Good. What is VE?
Minute ventilation.
Minute ventilation?
Minute ventilation. So using a respirometer, how would you instruct your patient? What would you have your patient do to measure their VE?
Have them take a deep breath and blow, 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 blow.
No, what is VE?
That's it.
Let's go back. So VE is minute ventilation. What does that consist of?
Dead space times
Oh,
No, not dead space.
Tidal
tidal
volume?
volume.
Vital volume
they kind of, yeah.
times
Respiratory rate.
times respiratory rate. So if you handed a patient a respirometer, what do you want them to do in order to get the amount of air that they move over the course of a minute?
You want them to breathe normal.
Breathe.
I hear rumblings, but I can't make out what y'all are saying. I'm sorry.
Don't you let them breathe 3 times? Like you calculate it 3 times as they're breathing, a regular breath?
So have them take 3 normal breaths.
And then don't you stop it after each time?
So have them take 1 normal breath.
1
3
normal, and
times.
then the breath, and then 1 normal. I think that's how.
Well, 1 normal breath is what volume of air? Is that how much air they moved over the course of a minute, or is that a tidal volume?
That's their tidal volume, but then you
Right,
multiply
we're
by
looking
3.
Or
The
is it how much
respiration.
air they move over the course of a minute. So let them breathe for a minute, right? Have them breathe normally for a minute, count their respiratory rate, then you can divide. Or really, if you're looking for your tidal volume, if you just want to know their minute ventilation, how much air they move over the course of a minute, let them breathe for a minute. That respirometer, remember, it's going to measure the volume of air with each breath. So if you let them breathe for an entire minute, that's going to measure in totality how much air they move over the course of a minute, which is exactly your minute ventilation. Does that make sense?
Yes.
Okay. So that's how you would instruct the patient for you, because of course it's patient driven. You can only measure what they're doing. So you have your patient just breathe normally for a minute. If you wanted to take it a step further and get their tidal volume then of course you would count their respirations, then divide that whole minute ventilation by their number of respirations, and that will give you the average for 1 breath. So that will give you that tidal volume.
Mm-hmm.
Any questions about that? The formula to determine alveolar minute ventilation is that will be your tidal volume minus your dead space. That will give you your alveolar volume. Multiply that by your respiratory rate, and that gives you your alveolar minute ventilation. Remember, a volume is 1 breath. Multiply that by your rate, and that gives you the amount of air moved over the course of a minute, or a minute ventilation.
Oh gosh, that's funny.
Sorry. Shunting can be caused by which of the following? Okay, so shunting.
After I picked my answer, I saw ANC. I'm like,
Can be caused by,
got me on that one.
of course, a decrease in ventilation,
Yeah.
or a decrease in perfusion. So it's a mismatch between the two, of course. And so what's the definition of shunting?
Decreased ventilation with increased perfusion.
Okay, that's what those two say, but what's the textbook definition of shunting? Is it ventilation in excess of perfusion, or perfusion in excess of ventilation?
Perfusion without an excess of.
Right, perfusion in excess of ventilation. So not enough ventilation to match the perfusion, which is why either a decrease in ventilation or an increase in perfusion can cause it. Does that make sense?
Yes.
Okay, so extra perfusion, too much perfusion, not enough ventilation, which is why these two things can cause it. But again, by definition, it's perfusion in excess of ventilation. Okay. What about dead space? What's the definition of dead space?
It's like wasted air, like gas that is not passed through the alveoli. Or,
Okay, so it's the opposite of something. That would be
Yeah.
ventilation in excess of perfusion. So you can say that it's wasted ventilation because the lungs are working, but there's not enough blood flow to allow gas exchange to happen. So it's a waste of ventilation.
yeah.
Okay, it's like you could say that shunting is a wasted perfusion because this blood is going by the alveoli, but the alveoli aren't filled with air, so they can't allow for gas exchange. So what can be a cause of shunting?
If a patient has carbon monoxide poisoning? No?
Whole different ball game.
Oh, okay.
Yeah, nuclear perfusion is okay. The alveoli are open, but it's just that the oxygen isn't bound, or the hemoglobin isn't bound to oxygen. It's bound to that carbon monoxide. So what can cause shunting? If shunting is perfusion in excess of ventilation or can cause by decreased ventilation, what can cause that to happen?
If you're fluid retention?
Tell me more. What do you mean? Like they got swollen ankles, retaining fluid, didn't take their Lasix?
Emphysema.
Okay, and why?
The
Go ahead.
you can go ahead.
The alveoli are full of mucus.
In what case?
And
So what can cause the alveoli to not be open or to not be able to participate in gas exchange?
Atelectasis?
Atelectasis, right? If your alveoli is a pancake, is it open? Can it participate in gas exchange? Nope. If it's filled with fluid, like pulmonary edema, so that's what I was getting at when you said fluid retention. I'm like, okay, where's the fluid though, right? Because if it's in your ankles, that's usually not going to cause a problem in your lungs. Now, if it's in your lungs, if you're in fluid overload, if you have what side of heart failure can cause pulmonary edema?
right side.
That's side. If the left, you have left sided heart failure that causes that backup to happen, right, into your lungs. So that can cause shunting. If your patient has pneumonia, right, they got a bunch of snot in their alveoli, that's not going to allow for gas to be exchanged throughout those snot filled alveoli. Consolidation, stuff like that is what's going to cause a patient to shunt. Emphysema is not a traditional cause, but emphysema, the disease process destroys the alveoli. Right? So that can impair gas exchange. So that's why I was asking you why, because emphysema by the nature of the disease does not, but if you break it down and say, okay, well, if it destroyed enough alveoli, then that could affect gas exchange. So those are some things that can cause shunting. Okay? And of course, things that can cause dead space would be things that hinder perfusion. So things that hinder ventilation are going to cause shunting. Things that hinder perfusion are going to cause that dead space unit. So a blood clot, cardiac arrest, decreased cardiac output, stuff like that. Any questions?
Okay.
Bringing back some memories.
Ooh.
Hopefully a little bit. Promoting some deep thoughts.
Yeah.
All right. So the normal value of ventilation and perfusion is right. Good. So you normally have the 4 liters per minute of alveolar ventilation. And again, like we talked about before, our normal, the absolute value, at least for our cardiac output, is about 5 liters per minute. What's the equation for cardiac output? This is on your math sheet I sent you yesterday. How do you calculate cardiac output?
Look at it.
This is even homework back in the day.
5 to 4 or 2. What is it?
What are the 2 factors that influence cardiac output? So cardiac output is how much blood that leaves your heart over the course of a minute, right? So what 2 factors influence cardiac output? Or what times what? Okay, I'll let y'all get back to me after you do the math. Let me know.
Okay.
Okay, what is the primary problem in obstructive lung disease? Good job. That would be increased airway resistance. So again, they can get the air in, no problem. They have very compliant lungs. Can't get the air out. Why can't they get the air out? Because there's increased airway resistance. Tests of pulmonary mechanics include all of the following except that would be your FRC. What's the difference between all these other tests, your MVV and your FEFs and your FEVs versus your FRC?
They all test flows and that one tests the capacity?
Right. So your FRC is a volume of air, it's a capacity. Whereas the other one are testing how air moves, the mechanics, the movement of the air in and out of your lung. Tell me about MVV. What do you have your patient do?
Breathe
That's
over the
right.
course of
Go
the
past
minute.
for 12 seconds.
Yep, breathe in as deep and as fast as they can for 12 seconds. What's the risk of doing this test?
They're more likely to pass out.
Yep, your patient will likely pass out. So your FBFs, what do they tell you? And what do you have your patient do? How do you get these values? What maneuver do they do to give you these values?
It's what I was saying earlier, having them blow.
Blow how? Blow into
It's
what?
in a spirometer. Is a maximum inhalation and then a forceful exhalation.
Like a right respirometer?
Yes.
Are you supposed to blow hard into a right respirometer?
Well,
Yep. You gotta bend the little veins inside of it, remember?
yeah.
So you never want any forced flow studies into a right respirometer. They're gonna use an actual PFT machine. You're gonna have them to do the flow volume loop maneuver.
That's what I was trying to
No.
remember.
Yep. Which is what the max inhale, max exhale,
Yeah.
and then inhale again. That's gonna give you that flow volume loop, right? FV maneuver, force vital capacity maneuver, really is what it is. And from there, you're going to get all these FEV1s and your FEV1/FEC and all your FEFs, the FEF 2575, FEF 200, 1200. And so got to have them do that flow volume loop, which is what maneuver? That's your FVC maneuver. Max inhale, max exhale, breathe in again to complete that loop. Okay. So make sure that when you go back and study your M&P, that you study both packets. Remember, you have one with like your formulas and your shunt and your dead space and all that stuff, and then you have another one with all of your PFT information in it. Even go back to your Butler homework and that sort of thing too. You need to. Which of the following is typically elevated and restricted lung disease? Yep, it's the pressure needed to expand the lungs. So remember, people with restricted disease, their lungs are not very compliant. Their lungs do not easily and readily accept volumes of air. So it requires more pressure to get air into those lungs. Think about one of those little tiny balloons that you get out of the pack. That's a restricted lung. How hard do you have to blow to fill that balloon up? Very, right? So that's a restricted lung. Okay, so what is ERV?
Expiratory reserve volume? Residual, what is it?
You're right.
Okay.
Expiratory reserve volume. And that's what's left in your lungs after a maximum exhale. Or I'm sorry. That's what you can exhale maximally after a quiet exhalation. So that can be worded different ways. So and if you look at your box, after your tidal volume, what volume is next? Your ERV. So after exhaling normally, that will be exhaling your tidal volume, the volume that can be exhaled maximally. So you exhale normally, then you take another big exhalation, you just exhaled your ERV, okay? So make sure you go back and study your definitions, and it can be worded slightly differently, but saying the same thing, okay? What PFTs presents the highest risk of fainting, Taylor? Good, so that's your NBV, because you're having your patient take max deep breath as fast as they can for 12 seconds. So of course that can cause your patient to faint. That's it. And your patient needs to perform the MVV or any test really at least 3 times, and 3 times that are within your normal margin of error. So you can't have, if you're doing minute ventilation, for example, that one time they got 2 liters, one time they got 10 liters, one time they got 7 liters. They need to be 3 acceptable results to make sure that it wasn't just a fluke, that you're getting kind of more so an average of what they're capable of. So any test, you need at least 3 attempts, 3 acceptable attempts. Which of the following volumes or capacities cannot be measured by simple spirometry? Good. Why can't they be measured with simple spirometry?
Can't measure your volume.
Right, because you can't measure your residual volume.
No.
FR contains your residual volume. but you can't measure that directly either. What other volume or capacity can you not measure via simple spirometry?
Total lung capacity.
TLC, good. And what does that mean by simple spirometry?
You can't use anything else but a PFT or the oh my gosh, the box.
Right. So you would have to use, that's one option, but you can't use a right respirometer. You can't use a little portable PFT machine. You would have to actually send them to a PFT lab that has the capability of measuring everything. So either a body box, what are your other two options for measuring your TLC, RV, FRC?
Is there something to do with nitrogen?
It's got something to do with it.
Nitrogen washout?
Nitrogen washout or another type of gas. Helium dilution.
Heliox.
Nope. Helium dilution.
Oh,
So
helium.
heliox is that mixture of helium and oxygen that you can give to patients for airway obstructions and stuff like that. Got helium in it. That's a lot of helium. Okay, number 20. After rest and expiration, the air still remains in the lungs. What is this volume? Good. So after a normal, quiet, resting, all those are synonyms, expiration, you still have air that stays in the lungs. And this was asked earlier, but just worded different. Left in your lungs, basically after your tidal volume, that's your ERV plus your RV, or however you want to say it, your FRC. Any questions about that? Which of the following is equal to your TLC, or total lung capacity? Here, that's your all. So if you remember your box, all four volumes equals your total lung capacity. So that's your tidal volume, your ERV, your IRV, and your RV. Okay, let's keep in our lead. He's got a hot streak. Which is the most common lung volume measured during spirometry? That would be your vital capacity. So remember, well, good, nobody picked total lung capacity. Good job. So what is your expiratory reserve volume going to tell you? If you measure that by itself, what would that tell you? Not much. It doesn't really it can't tell you very much information on its own. Neither can the tidal volume. So that's good to know, but that really doesn't tell you a whole lot about the patient, or as far as if they have a specific disease process, right? Because that's the point of doing these spirometry tests. That's the point of doing PFTs. So yeah, it might tell you, if your patient has an adequate tidal volume, to have an adequate minute ventilation, but that's not going to help you distinguish whether the patient has a restrictive disease or a lung disease, not definitively. But the vital capacity can. The vital capacity is the best indicator of what kind of disease process or what kind of disease.
Would that be the obstructive?
The other one.
Restrictive.
Restrictive. So vital capacity is the best indicator of restricted disease. What is the maneuver for vital capacity? How would you instruct your patient to do a vital capacity for you so you can get the measurement?
Would that just be having them inhale like a regular IF? Well, no.
And remember, with spirometry, you can't measure what they inhale. You can only measure what they exhale. So that's going to be a max inhale followed by a max exhale. Remember, it's important to know these techniques, y'all. So vital capacity is a maximum inhale, maximum exhale. People with restrictive lung diseases, they don't have very good volumes, very good capacities. So you have them, so you say to them, I want you to breathe in as deep as you can, completely fill your lungs, but I want you to blow all that air out. That volume is going to be very small in comparison to a person who does not have restrictive disease, which is why it tells us, whoa, their volume, the total amount that their lungs can inhale and exhale is significantly decreased. They must have restricted disease. So that's what the information that you're getting by looking at VC, which is why it's the most common lung measurement and it's the best indicator of restricted disease. Any questions? Okay. What's the normal IC? Good. That's 3,600 mLs or 3.6 liters. Well, to believe. What is the normal predicted vital capacity measurement in the adult patient? Okay, good. That is 4,800 mLs or 4.8 liters. If you wanted to know for a specific patient, how would you measure it or calculate it?
We would just do the what we just talked about.
Which is what? Talk about
We would measure by them doing a maximum inhalation and a maximum exhalation.
Okay, so that's how you would measure it directly. Okay, great. How would you calculate it? If I wanted to know what your vital capacity should be, how would I calculate that? How would I estimate what the range for your vital capacity should be?
Is it something to do with the ideal body weight?
Something to do with it.
Times 3? Well, it
Yeah.
depends on if you're a male or a female.
Well, yeah, because your ideal body weight, to figure out your ideal body weight, your formula would determine, well, the sex of the patient would determine what formula you use, yes.
So then we would do the 106 or 105 plus the,
Plus
would that
8.
be that one?
Well, that's
Right.
just to determine their weight, their
Okay.
ideal body weight. That still doesn't tell you their volume.
And then
So it's 65 to 75 milliliters per kilogram is their ideal body weight. That's what a patient's normal vital capacity should be.
okay.
Okay. All right, Taylor took the lead there. What's the normal predicted TLC for adults? Good, about 6 liters. Okay, which of the following conditions is TLC always reduced? That would be restricted disease, because again, they have problems getting air in. If they can't get the air in, then of course, the total amount that their lungs can hold is going to be decreased. Dead space is defined as ventilation in excess of perfusion. So again, shunting is perfusion in excess of ventilation. Dead space is ventilation in excess of perfusion. Any questions? All right, so it's back in the leads. Tagore here. The respiratory quotient refers primarily to
You are now muted.
that would be the unequal exchange for carbon dioxide for oxygen. So remember, respiratory quotient is referring to the respiratory gases. What are the respiratory gases? Carbon dioxide and oxygen. Okay, given a tidal volume of 400 mLs, dead space of 150, and a respiratory rate of 10, what is the alveolar minute ventilation? Good, 2,500 mL. So 400 minus 150 gives you 250 times 10 is 2,500 mL. Of course, your formula for alveolar minute ventilation, again, we asked earlier, was tidal volume minus dead space times the respiratory rate. So that's quick, simple mental math. Okay, gas exchange in the lung between the alveolar air and the capillary blood is that's external respiration. Normal adult value for vital capacity is that should actually only be 4.8 liters. So that should just be the blue one. 4.8 liters or 4,800 mLs. How do you calculate vital capacity for a specific patient?
I'm sorry, what did you say?
How do we calculate vital capacity for a specific patient?
Just said that.
Mm-hmm.
Oh God, we just said this.
Yeah.
Horrible. Max inhalation.
No, how do you calculate it? Not how, what's the maneuver? How do you calculate it? So if you know your patient's height.
Okay, the height. Oh, okay, hold on.
So one of the ideal body weight, so like 106 plus 6 times height minus 60 for
So
males.
So you figure out their ideal body weight in kilograms, and then what's the range?
65 to 75?
Right, and then for every kilogram they weigh, it's going to be between 65 and 75 milliliters per kilogram that they weigh. So to calculate tidal or vital capacity for any patient, it should be 65 to 75 milliliters per kilogram of their ideal body weight. Okay, but you would, of course, if this were a patient or on paper, you would have to first know their ideal body weight. How do you find a patient's ideal body weight? You use your ideal body weight formula, the 105 or 106, depending on if your patient is male or female. Any questions?
And then we would multiply that by the 60 to 70, right?
Right. 65 to 75. If the tidal volume and frequency remain constant, an increase in dead space will result in a decrease in alveolar ventilation. So you first have to remember what your formula is for alveolar minute ventilation. It's tidal volume minus dead space times respiratory rate. So if your tidal volume stayed the same, your frequency stayed the same, but you're subtracting out a larger number from your tidal volume, your answer is going to decrease. Does that make sense?
Yes.
Are there any questions about that?
No, ma'am.
So when compliance decreases and resistance increases, what is the effect or result? That would be an increased work of breathing. If your patient can't get the air in and they can't get the air out, it's going to suck for them when it comes to breathing. They're not going to be able to do it very easily. What's the normal value for RQ? Good, 0.8. What's the normal ratio for RQ?
4 to 5.
4 to 5. And if you're talking about in the case of milliliters, how many milliliters of oxygen, how many milliliters of carbon dioxide?
200 milliliters of oxygen and 250 of carbon dioxide? Or is it one of those?
Something about a 200 and a 250. More oxygen.
More oxygen, okay.
Okay, Reynolds number calculation is performed as 1500. How is this flow described? Okay, that would be laminar. What's your criteria for Reynolds number?
If it's less than 2,000, it's laminar. If it's if it's 4,000 or greater, it's turbulent. And if it's 2,000 to 4,000, then it's transitional or mixed.
Good. Or tracheobronchial. All
Yes.
those. Yeah, good job. Okay, is moving on up. The IC is equal to good. That's your IRB and your VT. Think about it. Your VT is a normal inhalation. Your IRB is a maximum inhalation after a normal inhalation. And of course, your inspiratory capacity is a maximum inhalation. So you could either look at your box, visualize your box, or just remember what each of those values are. Okay, which of the following is the best indicator of restrictive lung disease? We talked about that. That's your vital capacity. We won't start that conversation over again, but it's exactly what I said earlier. So interpret the patient's following PFT results. They have a TLC of 98%, FVC of 65%, and an FEV1 of 85%. What's wrong with them, if anything? Okay, so the best answer here is a mild pulmonary restriction. Reason being is because your vital capacity or forced vital capacity is the best indicator of restrictive disease. And this is below your 70, 75, 80, even benchmark, depending on what book you're looking at, significantly lower. So we can assume that they have a mild obstruction. Or I'm sorry, mild restriction, I apologize. Which term represents the most common cause of hypoxemia in patients with lung disease? Yeah, that would be a VQ mismatch or a VQ imbalance. Yeah, last one. Which statement is true regarding regional differences in ventilation and perfusion? Okay, that would be the yellow and the blue. So regional VQ differences are most evident in the upright position. That's the position we're in most often, and they're caused by gravity. And the upright position, gravity is bearing down on us. So the party is in the basement. You have much more blood flow in the bases of your lungs and much more perfusion also in the bases of your lungs. Diffusion, they happen from areas of high concentration to low concentration. So that's what makes the red one wrong, is because your arrows are going in the opposite direction. When things diffuse, it's like a ball rolling down a hill. It's going to go from a high starting point to a low starting point. Good job, Nicole. Good job, Flo. Good job, Taylor. Good job, AJ. And just say Al. Africa. Good job, guys. Any questions about MNP? I know that you all recall the struggles of MNP. It's everybody's favorite chapter. So if you struggled with that unit, you should be asking questions, or at least, again, y'all know how I always tell you guys, I'm not looking for eloquently stated questions, but at least things that you may need to go over, okay? So this is the time. Any questions, anything that we need to revisit when it comes to MNP?
I think I just have to go over them, because a lot of what my issue is, remembering those, what each of them still, even when you went over it, I still have to kind of go over it because my brain doesn't kind of want to.
You mean the volumes and capacities?
Mm-hmm. I understand the box and I understand all that, but still trying to think of, okay, I'm doing this, I'm doing that. What is that? I'm doing this, I'm doing that, and just trying to get that and just keep going over it.
And again, like we talked about before, knowing your box will help you, because even if you can't remember the exact definition,